Traditional silicon chips are rigid. They're flat, brittle, and designed for one thing, to sit still on a circuit board. But artificial intelligence is moving beyond data centers and laptops. It's moving into soft robots that bend and twist, into wearable patches that conform to skin, into systems that need to survive repeated mechanical stress. The problem is that rigid silicon doesn't belong in those environments. It cracks under pressure. It fails when bent. It breaks when it needs to flex. In February 2026, researchers demonstrated something different. A chip that doesn't just tolerate bending, it's designed to bend. It's called Flexi, and it represents a fundamental departure from how we've traditionally thought about integrating AI into physical systems. But before we get ahead of ourselves, let's be clear about what Flexi actually is, what it can do, and what it cannot. Flexi is a fully flexible AI chip. When we say fully flexible, we mean the entire computing system is built on a flexible plastic film substrate using low-temperature polycrystalline silicon (LTPS) thin film transistors, so it can bend without breaking. Unlike traditional silicon chips built on rigid crystal wafers, Flexi's architecture distributes computing elements across a plastic base that maintains its function even under repeated deformation. The chip contains approximately 10,628 transistors and is designed to perform inference, meaning it can run trained AI models locally on the chip itself, but it cannot train those models. This distinction matters. Flexi is not a GPU, it's not a data center processor. It's not meant to compete with high-performance AI accelerators in terms of raw computational power. It is a research-grade, ultra-low-power AI processor purpose-built for a completely different problem space. Its entire architecture prioritizes one thing above all else: physical flexibility while maintaining computational capability. The design choices, LTPS thin film, transistors plus a compute and memory architecture, are what make it practical on a flexible substrate at ultra-low power. This integrated approach allows the chip to process data and make decisions without the energy overhead of traditional computing pipelines, which is essential when operating on a flexible substrate that cannot dissipate heat as effectively as rigid silicon. The demonstration reported in February 2026 focused on durability under extreme mechanical stress. Researchers bent the Flexi chip more than 40,000 cycles of bending, including 180-degree bends, and folded it down to roughly a 1 mm radius without experiencing performance loss. AI inference tasks ran continuously throughout the testing, showing that the chip didn't just survive the bending, it functioned reliably while being bent repeatedly. This is not a minor achievement. Traditional silicon chips fail catastrophically under the same conditions. The crystal lattice cracks, connections between transistors sever, performance degrades irreversibly. Flexi's demonstration showed that this outcome is not inevitable. A different architecture, different substrate materials, and a different design philosophy can produce a chip that maintains functionality through extreme physical deformation. But the demonstration went beyond simply proving durability. Researchers tested Flexi on specific AI tasks and achieved measurable results. The chip successfully performed arrhythmia detection with up to 99.2% accuracy, identifying irregular heartbeats from electrocardiogram data. It handled motion tracking tasks, monitoring walking and cycling patterns with 97.4% accuracy. These are real-world relevant applications, not synthetic benchmarks designed to make the chip look good. The power efficiency was also measured and documented. In low-power mode, Flexi consumed only 55.94 microwatts, an extremely low figure that demonstrates the ultra-efficient design. The chip maintained stable operation over 6 months of continuous testing, proving reliability beyond just the mechanical stress demonstrations. Storage capacity was measured at 1 kilobit, limiting the on-chip model size but sufficient for specialized, optimized inference tasks. However, it's essential to understand what this demonstration does not represent. This is a research milestone. There's no announced commercial rollout timeline yet, even if the researchers discuss low-cost manufacturability goals, suggesting it could theoretically be mass-produced for less than $1 per unit. But the jump from research prototype to mass-produced commercial product remains substantial. Flexi is not moving to consumer devices next year. It remains in the research and development phase. To understand why Flexi exists at all, you need to recognize a fundamental constraint of rigid silicon. It cannot exist in environments where physical deformation is constant. Soft robotics often require continuous flexing. Wearable patches need to conform to moving skin. Biomimetic systems require joints and articulations that move through their full range of motion repeatedly. In all these cases, placing rigid silicon at the point of movement is problematic. Then you attach a rigid chip to a moving surface, one of two things happens. Either the chip breaks or the connection between the chip and the system fails. You can try to isolate the rigid chip with flexible wiring or mechanical dampers, but this adds complexity, increases latency, and introduces points of failure. Every extra component adds weight, power consumption, and points where the system can degrade. Flexi eliminates this problem by distributing AI computation directly where it's needed. If a soft robotic finger needs to make decisions about grip strength based on tactile feedback, the inference processor can be embedded directly in the finger structure. It bends with the finger. It survives the mechanical stress. It operates continuously without isolation mechanisms. This distributed approach has several practical advantages. First, latency decreases dramatically. Data doesn't need to travel to a remote processing unit and back. It's processed locally where it's needed. Second, power consumption drops. Local processing uses less energy than transmitting data wirelessly or through tethered connections. Third, the system becomes more self-contained. A soft robotic component with embedded Flexi processing can make autonomous decisions without external computation. This is particularly valuable in biomimetic systems designed to mimic biological structures. Biological organisms don't centralize all computation in a brain and then wait for signals to travel. They embed computational capability throughout their structure. Muscles have local sensing and decision-making. Skin processes information locally. Flexi allows artificial systems to approach this model of distributed intelligence. The realistic application space for Flexi is narrow but specific. Biomimetic robotics represent one clear direction. These are artificial systems designed to replicate biological structures and behaviors. A research team developing an artificial hand that mimics human finger movement might embed Flexi chips at multiple joints. Each joint would have local sensory input, local processing, and local control, mirroring how biological fingers operate. Wearable health monitoring is another direction being explored. Medical patches that adhere to skin and monitor vital signs need to survive constant movement and deformation. Traditional rigid chips don't belong in this application. Flexi-based patches could integrate sensing, processing, and decision-making directly into the flexible substrate, eliminating the need for rigid components that shift and fail as the skin moves. The demonstrated arrhythmia detection capability makes this particularly relevant for cardiac monitoring applications. Soft robotics for medical and research environments represents a third area. Surgical robots that need to operate in confined spaces require flexible components that can navigate complex geometries. Research robots designed to interact with biological systems without damaging them benefit from soft, flexible construction throughout. Flexi enables these systems to include local processing capability where it matters most, but here's what needs to be emphasized. These are experimental and research-directed applications. They are not mass-market products launching in 2027. They are not consumer devices appearing in stores. Flexi is a research tool that addresses specific, specialized problems where rigid silicon genuinely cannot function. The use cases exist, but they exist in laboratories and research environments, not in mainstream consumer applications. Flexi achieves flexibility by accepting profound limitations in other areas. With roughly 10,600 transistors, the computational capability is severely constrained compared to conventional processors. A modern smartphone contains roughly 15 billion transistors. Even a modest embedded processor contains hundreds of millions. Flexi is operating at a scale where computational tasks need to be extremely specific and highly optimized. Flexible electronics typically face constraints in performance, density, and thermal handling compared with rigid silicon, so the trade-off is real. The chip cannot handle high-intensity computation that generates substantial heat. This forces researchers to optimize aggressively for power efficiency and narrow application scope, which means accepting significantly lower computational throughput than conventional processors. Manufacturing Flexi is fundamentally harder than manufacturing conventional chips. The materials are different. The processes are different. The substrate itself, flexible plastic rather than rigid silicon, introduces manufacturing variations that don't exist with crystalline semiconductor wafers. While researchers suggest the chip could be produced for under $1 at scale, actually achieving that scale in manufacturing is a separate challenge. Current production remains at the research and prototype level. These are not problems to be solved in the next product iteration. They are inherent to the approach. You cannot make Flexi operate at the clock speeds of a modern GPU without sacrificing flexibility. You cannot achieve the transistor density of conventional chips without returning to rigid materials. Flexi represents a deliberate choice to optimize for one dimension, physical flexibility, at the expense of conventional performance metrics. Flexi doesn't replace conventional AI chips. It doesn't compete with them. They operate in entirely different problem spaces. Conventional AI processors excel at high-throughput computation in stable, controlled environments. Data centers, cloud infrastructure, training pipelines. These are where rigid silicon thrives and will continue to dominate. Flexi addresses problems that conventional chips cannot solve. It's not about raw compute performance. It's about physical integration into systems where rigidity is incompatible with function. When the question is, how do we add AI AI capability to a soft robotic system, the answer is not a more powerful conventional chip. The answer is a fundamentally different approach to hardware design. This means Flexi complements existing AI infrastructure rather than replacing it. A biomimetic robot might use Flexi processors for local decision-making at joints and actuators, while communicating with conventional AI systems for higher-level planning and learning. A wearable patch with Flexi might handle continuous monitoring locally while occasionally uploading data to cloud systems for deeper analysis. They work together in a distributed intelligence architecture. The significance of Flexi lies in expanding the design space for AI applications. It demonstrates that intelligence doesn't have to be centralized in rigid processors on circuit boards. It can be embedded directly into physical structures. This opens possibilities that were previously closed. The broader context here is important. Artificial intelligence has been predominantly computational, algorithms running on processors. But the next frontier of AI is embodied AI, systems that interact with the physical world, that sense continuously, that adapt to dynamic environments. These systems need intelligence distributed throughout their structure, not centralized in a box. Traditional rigid silicon limits this possibility. It can be attached to robotic systems, but it remains fundamentally separate from the system itself. It's an external processor connected to mechanical components. Flexi changes this by making the processor itself a structural element capable of bending, flexing, and deforming while maintaining function. This is not about making AI smarter. It's about making AI possible in places where rigid silicon simply cannot survive. It's about enabling hardware designs that were previously impossible. It's about taking AI out of data centers and embedding it directly into the physical systems that need it. The development of Flexi indicates that the hardware landscape for AI is diversifying. We're not moving toward a single, universally optimal processor. Instead, we're developing specialized hardware for specialized problems. High-performance GPS for training, efficient inference processors for mobile and edge devices, and now flexible processors for embodied systems. Flexi represents a new direction in hardware design, not a performance race. The chip is demonstrably functional across real-world tasks, from cardiac monitoring to motion tracking, but it's also demonstrably limited in raw capability compared to conventional processors. The achievement lies not in competing with conventional processors, but in solving a problem they cannot solve. As artificial intelligence moves beyond software into physical systems, hardware constraints become increasingly important. The chips we design must fit the environments where AI needs to operate. For many of those environments, soft robots, wearable systems, biomimetic structures, Flexi points toward a solution. Not a complete solution, not a mass market solution yet, but a genuine step forward in making AI practical in places where rigidity was previously mandatory. The real significance of Flexi is this. It proves that flexibility is a hardware problem with hardware solutions. It proves that different constraints can produce genuinely different architectures, and it proves that the future of AI hardware isn't singular, it's plural, different chips for different problems, different materials for different environments. This chip doesn't make AI smarter, it makes AI possible in places where rigid silicon cannot exist.